Hello, welcome to Maths with EJD. In this video, I'll be talking about conditional probability. So let's go. So what is the definition and concept of conditional probability? For starters, conditional probability is the probability of an event occurring given that another event has already occurred. So this bears a bit of resemblance with dependent events that we considered in the second video, but of course a bit of we are going to see how this one is different from that. So conditional probability is denoted as probability of A given B. So the probability that A occurs given that B had already occurred. So this reads, which reads the probability of event A given that B has occurred. All right. So mathematically, it is defined. It is defined as probability A given B is equal to probability A intersection B divided by probability of B. Of course, probability A intersection B would come under multiplication rules. What like talking about second video on probability, talking about probability rules. So, and that can either be independent or dependent variables. Okay. So where P of A intersection B is the probability that both events A and B occur, and probability of P of B is the probability of event B occurring. That said, let's see an example. Okay, I guess I'm going to switch colors at this point. Consider a deck of 52 playing cards. 52 playing cards. Let event A be drawing a heart, and event B be drawing a red card. We want to find the probability of drawing a heart given that a red card has been drawn. Okay, so let's see how this goes. First of all, there are 26 red cards. There are 26 red cards in total. So there you have 13 hearts, and 13 diamonds of the 36 of the 26 red cards. 13 hearts and 13 diamonds. Okay. So one probability of drawing a heart given that a red card had been drawn. Okay, that's the first thing. Secondly, the probability of drawing a heart, is, of course, that's event A, right? That's event A. That is probability of A is equal to 13 over 52. That's also 1 over 2. Or we can leave it like this for now because we have other things ahead. So it's better to leave it in this raw form so we can simplify at the end of the day if necessary. So then the probability of drawing a red card, probability of drawing a red card, probability of drawing a heart is actually 13 hearts out of 26, out of the whole of 52, actually. So the probability of drawing a red card, which is event B now, that's event B, is actually P of B, and that is equal to 26 over 52. So that's we have 26 red cards in total. So that goes. Now, to find probability of drawing a heart given that a red card had been drawn. Given that a red card had been drawn, is actually will be as follows. Of course, we know what the formula looks like. So we need the probability that of A intersection B. So that's first, we have probability of A intersection B. That is a heart and a red card together. So that's probability of drawing a heart that is a red card. That's probability of drawing a heart, of course, which is also red. So that is equal to 13 over 52. Then the probability of B, the probability of drawing a red card altogether will be 26. That is 26 over 52. So finally, we have probability drawing a heart given that a red card had been drawn. It's probability A intersection B all over probability of B itself. So probability A intersection B is actually 13 over 52. That's 13 over 52 divided by probability of B, which is 26 over 52. So that is 13 over 52 times 52 over 26. Since we are dividing, so this is 13 over 26, or if you like, that is 1 over 2. So the probability of drawing a red heart, given that a red card had been drawn, is 1 divided by 2. So that goes. So that with that we come to the, that's the definition and concept behind conditional probability. Now let's look at some associated ideas. For instance, let's consider the law of total probability. the law of total probability. So the law of total probability provides a way to find the probability of an event by considering all the possible ways it can happen. So if B1, B2, up to Bn are mutually exclusive, and exhaustive events. So that means they are independent of themselves, right? They're mutually exclusive and exhaustive events. If exhaustive means you can get all of the possibilities, then we can say that the probability that A happens is actually the summation from I equals 1 to n of probability of A given BI. So I mean BI can now be, so BI it can now have B1, B2, B3 up to Bn multiplied by probability of BI itself. Now, of course, you can see this as coming from where we started from. You know, we said the other time that probability of A given B is actually probability of A intersection B all over probability of B. Okay. I guess this won't fit in here. So let's just leave that alone. Okay. All right. So this is the law of total probability. So you can write this for any kind of event that are mutually exclusive and exhaustive. So let's take an example. Suppose a company has two factories. Factory 1 and factory 2. Factory 1 produces 60% of the company's products. And factory 2 produces 40%. The probability that a product from factory 1 is defective is 0.02, and from factory 2 is 0.05. So we want to find the overall probability that a randomly chosen product is defective. So in this case, we have to put in consideration the total probability of a product being defective, from both factories. So here the law of total probability is useful. So let me switch to this. So first of all, let's B1 be the event. Let it be the event that a product comes from factory 1. Okay. Then B2 be the event that a product comes from factory 2. And of course, what we actually need is A, the event. A is the event that a product is defective. A product is defective. So if that is the case, we can have the following. So we have probability of B1. That's the probability that a product comes from factory 1. And of course, factory 1 produces 60% of the product. So 60% is the same thing as 0.60. Yeah. So probability of B2, that's probability that the product comes from factory 2. That is 40%, which is 0.40. That's 40 over 100. Then we know that the probability that the product is defective, given that it comes from factory 1. We've been told before that the probability that a product from factory 1 is defective is 0.02. So that means probability that it is defective, given that it's coming from factory 1, is 0.02. And probability that it is defective, A is that the probability, the event A is the defect, is about whether it is defective, right? So probability A given B2. The probability that a product that comes from factory 2 is defective is 0.05, as we have in the question already. So if we put all of that together, we can go by the law of total probability. And the law of total probability, then we have probability that a product is defective is actually probability that a product is defective coming from factory 1 multiplied by the probability that the product comes from factory 1 plus probability that the product is defective given that it comes from factory 2 times the probability that the product comes from factory 2. So all that leads us to this, that probability of that the product will be defective, which is actually probability A given B1. We know that's 0.02. Probability that a product from factory 1 is defective, multiplied by probability that the product comes from factory 1, which is 60%, that's 0.60, plus probability that a product is defective given that it comes from factory B2 is 0.05, multiplied by the probability that it comes from B2 in the first place, that is 0.40. So if we tidy all of this up, we get something nice. So 0.02 times 0.6, that's 2 times 6 is 12, 3 decimal places, that's 0.012. 5 times 4 is 20, and we have 2 decimal places. So that is 0.02. And all of that is 0.032. 0.032. So the probability that a product will be defective is 0.032, or 32 out of 1,000. So it means 32 out of 1,000 products will be defective. So we can put it that way, or 3.2% of products are defective, or 32 per 1,000. You can interpret it in different ways. So we can say the overall probability that a randomly chosen product, is defective is 0.032, or, if you multiply that by 100, that is 3.2%, or if you like, that's 32 per thousand. I believe that's how per thousand is written. So instead of zero, double zeros, zero up and down. So you have zero up and double zero down. That's 32 per thousand. So it means 3.2 out of 100 products are defective, or 32 out of 1,000 products are defective. Okay, so that's lovely. The law of total probability taken care of. So the last part, of conditional probability we want to consider is a very important one, and that is the idea of Bayes theorem. Bayes theorem has come to be very useful even in artificial intelligence today. So let's look at Bayes theorem. Bayes theorem. So it has something to do with conditional probability. So Bayes theorem allows us to update the probability of an event based on new information. And that is why the theorem has been, it has been employed in areas like data fitting, parameter estimation, and all that. So because it allows us to update the probability of an event based on new information. So you got to talk about prior and things like that. So it is given by probability A given B equals probability B given A multiplied by probability A divided by probability B. So we have this kind of extension. So probability A given B is equal to probability B given A multiplied by probability A divided by probability B. So here we say where probability P of A is the prior probability. The prior probability. So that's like the initial situation you're dealing with. I guess I need to write this properly. Prior. So it's the prior probability of event A. Then P B given A is the likelihood. Of event B given that or given A rather, given A. And finally, P of B is the total probability of event B. We just talked about the idea of total probability. So we have all of that coming together. So you have a prior, you have the likelihood, the prior, which is the what you're looking for, which I mean, prior is A, right? The likelihood is B given A, and then you have the total probability of B itself. So let's look at this example for that. Okay. So consider a medical test. Consider a medical test for a rare disease. That affects 1% of the population. The test correctly identifies the disease 99% of the time. If the person, you see conditionality there, so 99% of the time, if the person has it. That is the idea of true positive. So it is detected when the person has it. That's true positive rate. True positive rate. And 95%, 95% of the time, if the person does not have it. That is true negative rate. True negative rate. Of course, true positive, 99% true positive means that there's a 1% chance of false positive. That is, it will tell you that somebody has the disease when the person does not really have it. But that's a slim chance, which is 1%. But then there's a higher false negative chance that it's possible that 5 out of 100 people will be positive, but then the system will tell you it's negative. That's false negative. Okay, so what we actually want to find is this. We want to find the probability that a person has the disease, given that they tested positive. So it's actually, so from the system, you can say that someone can test positive and not have the disease, though the chance may be slim depending on all the probabilities we've been given. So that's what we have for this. Okay. So let me do that by the side here now. So if we take, I guess I want to change. If we take A to be event that a person has the disease, and we take B to be event that a person tests positive. So there are two different things. So someone can have the disease and test positive. Someone can have the disease and not test positive. So again, we have the following. We have the probability that a person has the disease, which is 1% of the population has it. That's 1%, and that is 1/100, which is 0.01. Then we have probability of B given A. That's the probability that a person tests positive, given that the person has the disease. That is correct identification of the disease 99% of the time if the person has it. So that is 99%. So the person tests positive, given that the person has the disease. So that's 0.99. Then we also have false positive, right? This is true positive now. So false positive would be true positive is 99%. So what about the probability that a person tests positive, but whereas the person doesn't really have the disease? So so we have true negative, false negative, false positive. So, okay, the person has the disease, but then doesn't have it. So 95%, the person does not have it and test positive. So in that case, now that's going to be 1 minus 95% now. If true negative is 95, then that means that false positive would be 5%. That's 1 minus 95%. So I know this is a bit tricky now. This is really tricky. Yeah, this is really tricky. Okay, so false positive rate let's say false negative. Okay, we have false, false negative and true positive. The probability for true positive plus false negative would be summed up together to 1. So here and 95% of the time, if the person does not have it. So it means that if the person does not have it and it is not detected, it is detected as positive. So that's 1 minus 95%, which is 0.05. So this is really tricky. Then, of course, we have probability A complement. That's the probability that, even that the person has the disease. So if the person doesn't have the disease, the chance, 1% of the population has the disease. So only, so it means that 99%, I think it's better to do it like 1 minus 99%. Of course, that's 1 minus 0.99. Okay, sorry. This should be 1 minus 1%. So those who have it, 1%. So those who don't have it, that's 1 minus 1%, which is 1 minus 0.01, and that's 0.99. Of course, this is the same as 1 minus 0.95, and that is why we have 0.05. Okay, so I know this, we need to pay serious attention to this part. So this is false positive now. This is false positive rate. False positive rate. False positive rate. That means the person does not have the disease, but the system detects that they have it. So in that case, that is false positive. So, and that will be 1 minus 95%. So it means that the false negative would be 1 minus 99%. So with all of this in place, of course, this is probability of not having the disease. Now, this one now is probability of not having the disease, because only 1% of the population has it. Okay. So with everything that has been stated, we need to then calculate probability of B. That's total probability now. So we have first we need P of B. That's probability of B, which is total probability. That is the total probability of testing positive. That's PB. So that means we have PB equals probability that the person tests positive given that the person has it times probability that the person actually has it. A is the probability that the person has the disease. That plus probability that the person tests positive given that the person does not have it, multiplied by the probability that the person actually does not have it. So it means the probability of B now is probability of B given it as 0.99. This is 0.99 times probability of A. Probability of A is 0.01. That plus probability of B given A complement. That's probability of false positive rate. That means the person is detected to have it, whereas the person doesn't. So that is 0.05 times probability that the person does not have it. That is 0.99. Okay, so the probability of B now would be 99 times 1 is 9. So we have 4 decimal places altogether. That's 0.00. So that's 2 decimal places here, 2 here. So we have 0.0099 plus 0.05 times 0.99. So that is whatever we get there. That is 4 decimal places, 0.0495, and all of that results to 0.05 0.94. Okay, so that is P of B first, but that's not where we are going to. So that's P of B. Now we can apply Bayes theorem. Now applying Bayes theorem. Now applying Bayes theorem, we have probability A given B. Probability A given B, that means probability that the person is tested, the person has the disease, given that the person tests, the person has the disease, given that the person tests positive, yes. So that's what we are looking for again. We want to find the probability that the person has the disease, given that they tested positive, okay? So in that case now, probability of A given B is actually probability of B given A times probability of A divided by probability of B itself, which we just found. So that means the probability of A given B is equal to probability of B given A. We have that already up. That's B given A, that's 0.99. That is 0.99 multiplied by probability of A itself. Probability that somebody has the disease is 0.01 because 1% of the population has the disease. Probability of B is what we just found out, 0.0594. And that is equal to 99 times 1, that's 99. 3 decimal places, that's 4 decimal places, 0.099. 0.0099 all over 0.0594, and that is approximately 0.167. If you multiply that by 100, you get 16.7%. So now say that, therefore, the probability that a person has the disease, given that they tested positive, is approximately 16.7%. Of course, because you have 0.167 multiplied by 100, that's 16.7%, or 167 per thousand, like I like to say, 167 per thousand. So if you test 1,000 people, 167 of them if 167 so the probability that a person has the disease, given that they tested positive, is approximately 167 out of 1,000 people, or 16.7 out of 100, basically. All right, so let's quickly look at some practical applications before we round off. So let's look at some practical applications of all these things. Practical applications of whether it's Bayes or all that. So of course, from what we just saw now, we can see that we have this applied to medical diagnosis. Okay, so medical diagnosis. So you see that Bayes theorem is used to update the probability of a disease based on test results. Considering the prevalence of the disease and the accuracy of the test. So of course, this is exactly like what we just the problem is solved. The prevalence of the disease and the accuracy of the test. We have Bayes working for that. Then we can have we have that coming up also in spam filtering. filtering. I mean, it's a big issue with our email systems. So conditional probability helps in classifying emails as spam or not, based on the occurrence of certain keywords. All right. And of course, we have decision making. Of course, I mean, the things we have looked at already, they are decision making, whether it's a medical diagnosis or spam filtering, they're actually decision making. Well, I mean, but we have it in other areas. For instance, in finance, conditional probability, conditional probability helps in making investment decisions by accessing risks and returns based on new market information. So it's all about updating information, right? Based on new market information, because all this information gets updated from time to time. So you see, these concepts are fundamental in statistics and probability, providing tools for analyzing and interpreting data in various fields. So that brings us to the end of conditional probability. And you see that the peak of conditional probability is the idea of Bayes theorem, which has found a lot of use in so many fields, including the hot potato idea of artificial intelligence. Thank you so much for listening thus far. If you have not subscribed, you definitely want to do that at this point. And of course, you want to hit the notification bell so you can always get alerted when a new video is released. Then don't forget to comment, like, and share so more and more people can get informed, can get to know some of these concepts. Bye.